factorials lend themselves quite nicely to proof by induction questions. So we're going to have a look at a few proof by induction questions that use factorials. So using the same structure as we saw previously, the first step is always the base case, which in this case is when n is equal to 1, because we're in the positive integers. So when n is equal to 1, the left-hand side of this equation is going to be the sum from r equals 1 to 1 of r times 2 to the r over r plus 2 factorial, which is equal to, well, it's the sum of one term when r is 1. So it's 1 times 2 to the 1 over 3 factorial, which is 2 over 6, or 1/3. On the right-hand side, we have 1 minus 2 to the power of n plus 1, which is 2, over 1 plus 2 is 3 factorial. And this gets us 1 minus 2 squared is 4. So 1 minus 4 over 3 factorial is 6. So 1 minus 4/6, which is equal to 2/6, which is equal to 1/3. So the base case holds. When n is equal to 1. Step 2, when n is equal to k, is our assumption. So we are going to assume that the sum from r equals 1 up to k of r times 2 to the r over r plus 2 factorial is equal to 1 minus 2 to the k plus 1 over k plus 2 factorial. So that's our assumption. Step 3, I just realised I didn't write a 2 there, let's put that in. Step 3, n is equal to k plus 1, our inductive step. Now I'm going to write down what I want to show, not because this is worth any marks, but because it makes it clear what I'm trying to do, both to me and the reader. So r equals 1 up to k plus 1 of r times by 2 to the r over r plus 2 factorial is 1 minus 2 to the k plus 2 over k plus 3 factorial. That's what I'm trying to show here. So I'm going to start with the left-hand side of that. And I'm going to break that sum up into the sum of the first k parts plus the k plus 1th term. So substituting k plus 1 into this, I get k plus 1 times 2 to the power of k plus 1 over k plus 3 factorial. But this thing is my assumption from up here. So this bit here, I'm just going to replace with that because it's equal to that from the assumption. So it's 1 minus 2 to the k plus 1 over k plus 2 factorial. And then I've still got on the end plus k plus 1 times 2 to the k plus 1 over k plus 3 factorial. Now I've got to try and simplify this into this. Now notice I've already got the 1 minus at the beginning, so I'm going to leave that 1 minus there. I don't want to get rid of that. And so 1 minus something that needs to simplify to this, so that something is 2 to the k plus 1 over k plus 2 factorial minus k plus 1, oh, I'm missing 1 there, times by 2 to the k plus 1 all over k plus 3 factorial. Now, trying to simplify that expression in the brackets there, I need a common denominator. The common denominator between k plus 2 factorial and k plus 3 factorial, let's just think, what would the smallest thing be? Now, I could do k plus 2 factorial times k plus 3 factorial, but I don't really need to. Let's think about a number. Let's think about 4 factorial. I had that as a denominator, and 5 factorial. Well, this is 4 times 3 times 2 times 1, and this is 5 times 4 times 3 times 2 times 1. So actually, the common denominator in this case would be 5 factorial. And all I had to do was multiply this one by 5. So if this was a, this would be 5a. So I'm going to do something very similar here. What is my common denominator going to be? Well, my common denominator here is going to be the k plus 3 factorial. But to get that on the denominator here, I've multiplied k plus 2 factorial by k plus 3. So I need to multiply the numerator by k plus 3 as well. And then this one, I haven't actually had to do anything to it because it's already got that as a denominator. Okay, now, combining those two fractions, I've got k plus 3 times 2 to the k plus 1 minus k plus 1 times 2 to the k plus 1. Again, let's have a think about what that is. That is, I've got some k plus 3 lots of something minus k plus 1 lots of something. The difference between k plus 3 and k plus 1 is going to be 2 lots of something. Now, there are multiple ways I could reason that. I can reason it from there, but we might also want to show that a little bit more. Maybe I factorize out the 2k plus 1. Maybe I expand. There are multiple different ways to approach this. Let's go for the, I suppose, most straightforward, which would be to multiply out. So I'd get k times 2k plus 1 plus 3 lots of 2k plus 1 minus k lots of 2k plus 1 minus 1 lot of 2 to the k plus 1. And all of that is over k plus 3 factorial. Hopefully you can see that's going to cancel with that one. And 3 lots of 2 to the k plus 1 minus 1 lot of 2 to the k plus 1 is going to leave me with 2 lots of 2 to the k plus 1 over k plus 3 factorial. But 2 lots of 2 to the k plus 1 is going to be 2 to the k plus 2, because this is 2 to the power of 1, hidden power there. And then we add those indices to get 2 to the k plus 2 over k plus 3 factorial. And actually, if we look back up here, that is exactly what we were trying to show. So that is equal to the right-hand side. So we have shown this statement to be true, and thus completed the proof by induction. The one thing that is left is to do our conclusion. So step 4 is our conclusion. And our conclusion, remember, says something along the lines of hence, by mathematical induction, since it is true for n equals 1, and if it is true for n equals k, it is also true for, let me just do that so it doesn't go off the edge of the video, n equals k plus 1, it must be true for all n in the positive integers, which is what we were trying to show. And we complete the proof by induction. This is a good example of factorials being used in a proof by induction question. we had to use a few things that we know about factorials. So here, finding the common denominator, we had to use the factorial idea. We also had to obviously use factorials a bit further up. We also had to use our knowledge of factorizing and algebra skills here, which was very important. So it's a common idea to use factorials in these proof by induction questions, and definitely something that's worth reviewing.